Alright, now we're going to do problem number 2 of homework number 8. Problem number 2 is basically a derivation of the semi-random telegraph signal, which we saw in our notes. Let's just go through it. It actually has a total of 4 parts, A through D. So let's see what we have given. We let n be the Poisson with a parameter of lambda. We've seen this in our notes. So basically the probability of n, which is the number of random points that arrive within the interval between t1 and t2, is equal to k. Alright? And we define this probability in terms of our Poisson equation, which is basically e to the negative lambda times the difference of our time within our interval, the time points, t2 minus t1. Then right here we actually multiply it times lambda times this product, lambda times the difference of our times, all to the k, which is number of random points at arrival, all over the k factorial. Furthermore, we define a stochastic process for our equation. So basically, we define a variable x in terms of t time. The way we actually define this here is that we define it as 1 if the number of random points is odd between time point 0 to some random unknown time point, and we define it as -1 if that n is even within that interval between 0 and t. And the problem gives us kind of a basic breakdown of how we define x of t right here. Okay? Now, what the problem asks us is to find the probability of our stochastic variable, our stochastic process, when basically it's equal to 1, or basically when n is odd. Alright? And we'll show that basically there's going to be a similar way to show the probability when x is equal to -1 or when even. That's going to be important for the next parts of our problem for B and C. But let's start with the actual question for part A. Okay? Now, let's see what we have here. If we're looking for the probability of x is equal to 1, we basically I'm just writing it out for clarity. We're looking for the probability within the interval from 0 to t that k is odd. Alright? So basically k is going to be equal to 1, 3, 5, 7, 9. So it's basically the sum of all the probabilities where k is odd. Alright? Which we can substitute. We use the actual Poisson equation. And if we actually create the series expansion of this, okay, I misspoke. We actually expand the sum right here. I'm jumping ahead by saying series expansion, but we actually break this down. This right here we can bring to the outside, and this sum expands. Basically, if we're looking only at k is equal to odd, so this when it's 1, that term. When k is 3, that term. K is 5, it's that term. 7, so on. So that's what we're looking for in this term. We're looking for something to define this equation. Now, at this point, we actually have to take a step back. How do we actually define this? Now, in order to define this, we have to do a small side note. Basically, we can show that we can get this equation, but first we have to look at the definition for the hyperbolic function, so sine h, in terms of lambda t, and also we look how that's related to the series expansion of e to the lambda t. Now, by definition, we can actually series expand e to the lambda t and make it 1 plus lambda t plus lambda t squared over, lambda t squared over 2 factorial, and so on and so on. Alright? That's basically the definition. So it's basically always the next term. This is going to be 0 terms, 1 term, the second term. Basically, it's going to be some n over n factorial. That's our expansion. Equivalently, we can actually show that if our expansion were negative, so we actually had a negative term, that basically every odd term would be have a negative sign in front of it. So since this is our 0 term, it's going to be positive. This is going to be our first term. All right, so it's basically lambda t to the first over 1 factorial. Basically, because we have this negative term, this ends up being a negative. This is our even term. It's going to be positive. This is going to be negative, positive. I mean, we can basically see this definition, how it works out. Now, what we notice, which is interesting, is that if we take the difference of these two, this minus that, I mean, look what happens. We take the difference, so this minus that, these two cancel. The ones cancel. This minus the negative that, that's basically going to end up being this term times 2. The even term here cancels. The odd term here stays there times 2. Even term cancels, odd term times 2. So what we end up with is this term right here. Notice how that's very similar to this inner term right over here. Alright? It's just basically multiplied by 2. In fact, we could basically define this inner term by e to the lambda t minus e to the negative lambda t over 2. Alright? Similarly, if we'd actually added these terms instead of subtracting, we would get the opposite right here. We would have basically gotten 2 times, and we would have gotten even terms. We would have ended up with, 2 times, we would have ended up 2 times, and the expansion would have been 1, the lambda t over 2 factorial, lambda t to the 4th over 4 factorial, and so on. That becomes important for another reason in the moment, okay? Because that's basically how we would actually get, if we were working for the probability of x equal -1, we would have had an inner term that would have been similar, except it would have been on even terms, and basically that would have ended up being the sum over 2 instead of the difference. But right now we're working with this difference. Now, we know by definition that the hyperbolic function, all right, is defined like this. So it's defined by this term divided by 2, which if we bring this over here, I just didn't write it out, but the hyperbolic function is defined by this term. So basically, the hyperbolic sine of lambda t is equal to this, right here. And like I was describing earlier, it's like we could actually say that if we had done the -1 here, that we would have said that the expansion would have actually, we used the hyperbolic cosine. But we'll get to that in a minute. Let's stick to this right now. Basically, if we take all these terms, what we're going to end up saying is that this, which is equal to that, which is also equal to this term divided by 2, which is going to end up equal to this expansion. So that's great. We can actually plug in the hyperbolic sine into this above equation right here. All right? Basically, our probability of x of t equal to 1 is going to be equal to e to the negative lambda t times the hyperbolic sine function of lambda t. And if we want to break that down, we can substitute this in. We can actually show it in terms of e directly. It ends up being this, which we can actually figure out to be 1 minus e to the negative 2 lambda t over 2. All right? Right here I put as a note how we can equivalently use this. I mentioned this throughout a little bit. It's important for part B, but if I wanted to find the probability where it's -1, all right, this ends up being the sum, all right, which is basically the hyperbolic cosine. All right, we can actually do all the work here, but basically how it ends up working, if we take the sum, we're going to get even terms for our expansion. Then when we actually substitute it in here, we're going to get e to the negative lambda t times this term right here, all right? And this term, by definition, is just equal to the hyperbolic cosine. So I mentioned that here because the next part of our problem, part B, asks us to find the expected value of x in terms of our variable x. And the way we actually do that is basically we take the probability when x is equal to 1, multiply times our times 1, plus the probability when x is equal to -1 and multiply times negative 1. And because of what we showed, we can actually say this is the answer for part A, right there. This would be the answer for that term right here. We subtract it. If we actually use the definitions, we can break this down further right here. All right, as you can see, what we end up doing right here, we keep this on the outside. If we subtract terms, these two terms cancel out. we end up with a negative 2e to the negative lambda t over 2. The 2's cancel out. And our final answer is going to be negative e to the negative 2 lambda t. So that's the answer for our expected value of x in terms of t. Next, we're going to look at the autocorrelation in terms of t1, t2. That requires us to look in when t2 is greater than t1, and then when t1 is greater than excuse me, right there. Yes. Sorry about that. This is going to be when t1 is greater than or equal to t2. Okay? Both the equations are going to be equivalent. We can actually see this. I didn't write it fully out, but let's just start with t2 being greater than or equal to t1. By definition, it's going to be the actual product of our x variable in terms of t1 times our x term in terms of t2. Definition of our autocorrelation. All right. So basically, if we break this down, what we can actually do is that this ends up just being the probability, because we can actually show this. This ends up being, because there's two possibilities here, we can do it in terms of the probability of the sum of the two probabilities, where the probability is such that this product is equal to 1 and that this product is equal to negative 1. So we actually break it down like this. If we substitute in our terms for these probabilities, which we got above, we substitute this in right here. It's negative 1, so bring it down. This is the term, the cosine term that I mentioned. All right. Because what we figured out right here, all right, we can actually bring this down right here because we actually figured it out. Because if we factor out this term, which we did, this is going to end up being the hyperbolic sine of this term right here, minus the hyperbolic cosine, which we kind of basically did here. It's going to end up being this term. It's going to be e to the negative lambda times this difference, or what we sometimes call tau. So if we work this out, we can see these two terms are the same. So they're basically, when we multiply them together, we just multiply times 2. So our final answer is going to be e to the negative 2 lambda times the difference t2 minus t1. Now, if t1 had actually been greater than t2, this will be exactly the same. The only difference is that this difference is going to be flipped. It's going to be t1 minus t2. So our final answer for the autocorrelation here is going to end up basically being e to the negative 2 lambda times the absolute value of the difference between the two time factors. All right. Finally, they ask us, is our x variable WSS? No, it is not, because in order to be wide set stationary, we need this to actually have, this is our expected value of x needs to be a constant, and this has to be written in terms solely of tau. While our autocorrelation is written solely in terms of tau, as we can see up here, our expected value is not a constant. It varies according to t. So this is not WSS. Hence ends problem number 2 of homework 8.